Okay, this lesson should start the notes that are titled Standard Deviation and the Normal Distribution. This particular lesson is going to focus on the standard deviation, and we're going to begin by contrasting standard deviation with the statistical measures that we've already covered, namely the mean and the median. So we did this in a previous lesson. We covered what mean and median were, and they are measures of the center or the middle of a data set. They are calculated differently. There are pros and cons to each of them, and which one of those measures you want in any given situation depends on what element of the data you're trying to interpret. And a lot of times you actually want both measures of central tendency. You'd actually like to look at them both because whether they're close together or far apart can tell you things about your data set. But we can also measure how spread out a set of numbers is. So the second blank there is spread out. And as usual, I'm not going to be able to fit it on here on the video, but you should be able to with no trouble. Okay, we can also measure how spread out a set of number is using measures of dispersion. So the word you want in there is dispersion. So just to make it like a high school example, hypothetically, if there were a fight happening in the courtyard, a crowd of students will often gather, and then security shows up and they try to disperse the crowd. So disperse the crowd means get them out of that big clump, that big congregation, and send them to wherever it was that they were supposed to go in the first place. So the word disperse has to do with being spread out. And so a measure of dispersion tells you how spread out a set of numbers is. Now, there's a couple of like vocab things in here that like one of them is a typo, so I'm going to have you make a correction to your handout as I'm filling this out here. So two of them are things called variance, and the other is standard deviation, and that's the one we're going to talk about today. Standard, and there's not a chance the word deviation is going to fit on here, but standard deviation are both measures of, and then that should be the word dispersion there. Right. There we go. That's a little bit better. The symbol for standard deviation is, and I don't think I can make it visible in there. Now you can't really see it. I'll do it bigger down here. It looks like that. That is a lowercase sigma. Okay, so you might want to put that into your notes. You have a little bit of a space underneath there that you can write in. That is a lowercase sigma. Okay, we will talk about an uppercase sigma too. You will see uppercase sigmas in math as well, but that is a lowercase sigma. It looks a little bit like a cursive O, except without the loop-de-loop in it. And the symbol for variance is sigma squared. Okay, so just like, there we go. And both can be calculated by hand. Now, full disclosure on this, you don't really want to calculate either one of them by hand. We will do a class exercise where I will take you through the process of calculating standard deviation by hand, and then you'll appreciate the fact that that is not something you need to do. I'll also show you, for those of you that have graphing calculators, your graphing calculator will do the standard deviation for you. So pretty much what you do is you're going to enter all your numbers into a list, and you just have to learn which keystrokes, and the calculator will spit out your standard deviation. A lot of scientific calculators will also calculate standard deviation for you. I have a couple of scientific calculators that I've learned how to do it on, but I certainly don't have all of the scientific calculators. So if you'd like to know if your calculator does it or how to do it on your calculator, you might try looking it up on YouTube, or you can show it to me and I'll see if I can get you the right resources for doing that. All right, so we want to make sure that we have the contrast here. So mean and median measure where the middle of the data is, and variance and standard deviation specifically measure how spread out the data is. The bigger the standard deviation, the more spread out the numbers are. So let's take a look at this with an example. Here we have a couple of data sets. And this is a little bit awkward to do in video format, but I'll do my best here. So we have set 1, which is 20, 25, 25, 48, 55, 75, 80, 80, 87, 92, 95, and 98. And then we have set 2, which is 50, 55, 55, 57, 60, 62, 68, 70, 73, 75, 75, and 80. And the directions over there in the box say, find the mean or the average for each data set. So what I'll do here is you should pause the video and on your calculator, find the average for each data set. Make sure that that is something that you're getting some practice doing. I know it's a little bit tedious, but pause the video and take a moment to calculate that. All right, and what you should have noticed is that both data sets have an average. I'm not happy with that A. Both have an average of 65. Okay, and so that's what you should notice. So when you look at those two data sets, the middle of each data set is in the same spot. They both average together. Now the question is, which data set will have the higher standard deviation, and how can you tell? So maybe pause the video and think about that for a moment. Which one of those data sets has a higher standard deviation? Let me rephrase that for you. In other words, which is more spread out? Okay, and it's important to be able to interpret the question there. So which data set will have the higher standard deviation is another way of asking you which is more spread out, and then how can you tell? All right, and I hope that you actually did pause the video there. So what you should have answered is that set 1 is the one with the higher standard deviation because the numbers are more spread out. So you actually just kind of kick it back to the definition. So how do you know that? Because the numbers are more spread out. Take a look at them. In the first data set, your lowest number is 20. In the second data set, your lowest number is 50. The highest number in the data set, first data set, is 98 as compared to 80. So while they both had the same middle, data set 1 has more numbers that are further away from the middle than the second data set has. The second data set, all the numbers are clustered between 50 and 80, where the first data set has numbers that are both lower and higher than the second one. So what we've got here, let me bring, let's use a brown, is both data sets have an average of 65. And then what I did was I just did the standard deviation on the calculator. Okay, so you just have to believe me that I'm not leading you astray on this. The first data set, the standard deviation is 27.9. And the second data set, the standard deviation is 9.3. And so if you answered the first data set has the higher standard deviation, you answered correctly because 27.9 is obviously a lot higher than 9.3. So that's what standard deviation measures. And the whole point of this first part of the lesson is just to get a sense of what the number measures. Sometimes I define standard deviation this way. Okay, it is the second part of this lesson gets into the idea of how numbers are distributed. So we've got the idea of we have the sense of the center of the data, where's the middle, then how spread out are they? And then exactly if they're spread out, how are they spread out? Are they clustered? Are your numbers clustered in different places? So what I did here, it says we can draw pictures of how data is distributed by making histograms. Histogram is just, it's like a bar graph that shows quantity. Okay, so don't overinterpret that word. Let's make histograms of the data in the sets above to see how the scores are distributed. So I copied the data sets over. You should have your handout in front of you so you can actually still see the numbers. And so if my handwriting is really bad, it shouldn't be an issue. So the way a histogram works is it's pretty much a bar graph. And how you scale the bar graph depends on the data set. So for this one, if you look at like where the numbers are, we've got like numbers 20 through 90. This goes 50 through 80. You could, in theory, make this one a little bit smaller because it's not as big of a range of numbers. But because part of what I'm trying to show here is the contrast between set 1 and set 2, I'm actually going to scale them both the same way. So for set 1, because the numbers go from the 20s up to the 90s, I'm actually going to count by tens. You can count by ones, fives, tens, hundreds, that like whatever is a number that makes sense for you depending on the data. Don't get locked into thinking you always count by tens. And I'll try to show you why on the next slide. But we have numbers in their 20s, 30s, 40s, 50s, 60s, 70s, 80s, and 90s. And then for the purpose of comparison, I'm actually going to do the other one the same way. And you could contest whether that was really necessary to do them the same way. But for what I'm trying to do with the numbers, it makes sense. So the way this would work is, so I'm going to use X's. You'll hear some people do dots, and they'll call it a dot plot. And it's the same idea, except with dots. You can also, like I said, use bars, make it a bar graph. You get a lot of different options there. But as I look at my first data set, I've got 3 numbers that are in the 20s. And so I'm going to use 3 X's. If you're going to use X's or dots, like you do want to make sure that they're about the same size and that you're spacing them equally, because what you wouldn't want to do is 3 small X's there and then like do like 2 big X's over the 50 or something, because that will obviously defeat the point. I have no numbers in the 30s. I have 1 in the 40s, 1 in the 50s, none in the 60s, 1 in the 70s, 3 numbers in the 80s. And if I do this well, the column for the 3 X's for the 80s should be the same height as the column is the 3 X's for the 20s. And then I have 3 numbers in the 90s. Okay. And what that does is it gives you a visual representation of how those numbers are actually distributed. So we've got like a cluster down here and a smaller cluster down here and not a lot in the middle. Okay. So it might look something like that. The second data set, we have nothing in the 20s, 30s, or 40s. But then when we get to the 50s, we have 1, 2, 3, 4 values in the 50s. I have 1, 2, 3 in the 60s. 1, 2, 3, 4 in the 70s. And 1 in the 80s. And what you can tell from looking at this, and again, I wanted the scaling to be the same because I wanted the contrast between the two, but you can tell from looking at this what the visual inspection of the list of numbers already told us, which is that these numbers are clumped together more than these numbers. These numbers are more spread out. These ones are clustered together. And what we've essentially done there is we've made a picture of how the numbers are spread out. So a couple of things about that. When you're scaling them, and I don't know at the time that I'm recording this exactly what I'm going to have you do for classwork on this, but one of the problems in an existing classwork was something like this. Okay, and when students would do it, they would look back at their notes, which is good. That's what I want you to do. I want you to look at your notes. But the problems in the notes are scaled by tens. Well, if you try to do this and scale it by tens, okay, you can't plot anything on it, or they would all go into the same column, which defeats the point. So something like this, you would actually scale it by individual digits, and then you would do it this way. And so that's what I meant when I said you can pick the scaling that is going to work best for illustrating your data. Graphs, whether they're graphs on like the XY plane or whether it's histogram or whatever kind of graph it might be, the point of the graph is to take whatever you're looking at and turn it into a picture. And so you want to use the picture that's going to best be useful for whatever you're doing. Okay, so that brings us to the idea that there are different types of distributions. And that brings us to this. I got like a weird note in my hard copy of this. So notice how the data in the first set is more spread out than the data in the second set is more grouped together. This is why the standard deviation for the first set is higher. That's what I have in my notes, and that is referring to what in your notes is right above it, which is that right there. All right. When we plot data this way, we may find that it is skewed. And so we've got 3 pictures there. We've got positively skewed, which is this one over here on the left. We have negatively skewed, and then we have normally distributed. Now, just notice with the skew, like if you picture your number line and you've got like negative numbers to the left and positive numbers to the right, it's the skew is where like the tail is, not where the hump is. So positively skewed is going to be in the direction of where that like tail is. Negatively skewed is going to be in the direction in like on the left. Okay, not where the hump is, which for me anyway is backwards from what my intuition tells me it is, and my intuition is wrong. Now, what we're going to focus on in the next lesson is normal distribution. That is when actually the mean, the median, and the mode are all the same number, where the center of the data is like right here, and then it's actually evenly distributed in this nice, beautiful curve to the left and to the right. That is called the normal distribution. It's super, super common. It is also called a bell curve. And it is so important that it's going to get its own lesson with all kinds of, we're going to pull the standard deviation into it and look at the standard deviation of things that are on a bell curve. And then we'll look at z-scores. And then we only have one more lesson left in this unit. Now, just as an aside, I teach math class. You guys take tests for me. If you want to think for a moment, how do you think test scores are distributed in a math class? So we've got F's, D's, C's, B's, and A's. And I'll let you kind of chew on that for a little bit. Here is how your test scores are often distributed. It looks usually something like that. I usually have a healthy number of students in the A and B range. Not a lot of C's and D's. They're really like C's and D's are not super, super common. So if you're a student who kind of lands in that CD range a lot, you don't have a whole lot of company. And then lots of F's. And that's called an inverse bell curve because it's flipped over from the bell curve, like the normal curve. It's just kind of flipped over there. It's actually really, really common in a math class. So I tend to have, and it's not just me, it's math teachers in general, will tend to have like students that like know what's going on, and then students that are shooting in the dark all the time. So you should have on your filled in notes, you should have the front page. I'm not actually sure in the packet if it's like a front or if it's front and back, but you will not upload your notes yet. There is one more lesson on the normal distribution, standard deviation, integrating that, which is obviously the problems on the back before you will upload your notes into Focus. And again, that is specifically for the 2020-2021 school year.